So today's class is Computer Organization Module 4 Lecture 1. In this class, we'll learn how to design control units. We already know that the function of the control units is to generate a set of control signal and also to generate the sequence of the control signal. This control signal actually controls the whole system. System means it will control the different components of a computer. For designing the control units, there are two types of designing in a digital computer. One is called the hardware control unit. Another is called the microprogram control unit. Both are very important. From the name, you can easily understand that in the hardware control unit, there is no programming is used, and microprogramming control unit, there is a set of program is used for designing the control units. Today we will learn the hardware control unit. That means today we will learn how to design control units using the hardware. So before going to the designing part of the control unit, we will see here one simple digital computer, and we will see how they are connected with each other and how the control signal is generated from the generated for running the all the components. Now see here I have shown one simple digital computer. It has the different components. See what are the components here. The component is, first one is a program counter, you know, PC, then memory address register, MAR, RAM, random access memory, that is the main memory, memory data register, you all know what is the function of these different types of special purpose register, then ACC, that means the accumulator, then ALU, arithmetic logic unit, you will do the arithmetical and logical operation, then B is the general purpose register, IR is a special purpose register called instruction register, which stores the opcode of the instruction, and this is the control unit. Now see here, all the components are connected with a bus. Clear? Now in the system, here the size of the instruction is 12 bits. That means it uses that 12 bits bus. Out of the 12 bits, the uppermost 4 bits are used for generating the opcode. That means it uses the 4 bits opcode, and the lower 8 bits are used for addressing the operands. That means this is part is the left hand part is the opcode, and this part is the operand. Now each components are related with a set of control signals. Now see here, all are the control signals: IP, LP, EP, LM, R, W, LD, ED, LA, EA, AS, AU, LB, LI, and EI. All are the different control signal. Now what is clock? Clock is not actually a control signal. It will generate some pulse, and with the help of the clock, the control unit will generate the sequence of the control signal. It will generate the sequence of the control signal with the help of the pulse generated in the clock. Now see, in each of the components you can find out, mostly in each of the components you can find out two things. One is E, another is L. Suppose here EP, LP, here ED, LD, here EA, LA. Now, what is the meaning of E? E means data will come from register to bus. That means EP, that means the enable program counter, the data from the program counter, that means program counter is the address from the program counter. If this is activated, address from the program counter will go to the particular bus. That means it will transfer the data from program counter to bus if EP is activated. And another is L. L means the load. That means the data will be come from the bus to the particular register. Okay. Now suppose LP is activated. That means data which is in the bus will come to the program counter. If EP is activated, data which is in the program counter will come to the bus. Similarly, LM. LM means the data which is stored into the bus will come to the MAR. Okay. LD. The data which is stored into the bus will come to the MDR. ED. enable MDR. That means the data which is in the MDR will come to the bus. That's the reverse process. Clear? So these all are the different types of control signal. Now see here, what are the different types of control signal? Here, what is the total number of signal? 3 signals. 1, 2, 3. Here, one control signal. LM. Okay. Leave clock, because clock is not actually that type of control signal. It is generate the sequence. So here two control signals, RW. Here two control signals. One is LD, another is ED. Here are the two control signals. One is LA. Here EA. Here three control signals, S, A, EU. Here there is one control signal only, that is LB, load B. That means data will come from the particular bus to register B. If this is activated means 1. And here there are two control signals. If I add all these control signals, 3 plus 1 plus 2 plus 2 plus 2 plus 3 plus 1 plus 2, we'll get total 16 control signals in the system. That means this simple digital computer will generate 16 control signals. Now see here, in the 12-bit instructions, 4 is the opcode and 8-bit is the address. Now, how the control signal will actually transfer the data? You know, I have already told it that instruction means some register transfer operation. Okay. Now suppose we want to transfer the data from instruction register to program counter. Which control signal should be activated? That means 1. See here, instruction register to program counter, that means data will come from IR to the memory, to the bus, IR to the bus. That means EI should be activated, EI should be 1. Then data will come from IR to PC. That means data will be loaded from this bus to PC. That means LP will be activated. That means if computer wants to transfer the data from IR to PC, that means it has to activate the EI and it has to activate the LP. Okay. Similarly, suppose program has to transfer the data from PC to LM. Which signal should be activated? From PC to LM means PC data will be go to the bus. From the bus, it will be go to the MAR. So PC to bus, that means EP should be activated, EP should be activated, and bus to MAR, that means LM should be activated. So that means if I activate two signals, data will automatically come from PC to MAR. Clear? Similarly, if I activate EI and LP, data will automatically come from here to here. So these are called the data paths. Using on and off of the different signals, we can transfer the data from one component to another component. Clear? But we have to design this sequence. Sequence means after which control signal will activate after which control signal. Okay, this sequence have to generate using the control unit. So control unit generate the control signals, 16 control signals. All the control signals are required not at the time. Some have to be made 0 and some have to be made 1. Why 0? Because that is not required at that time. And all the signals that is required at that time, suppose in this case IR to PC, that means we require the signal EI, so EI should be 1 and LP should be 1. All other signals should be 0. So this sequence has to be generated by this control signal. Clear? Now there is another control signal IP, that is the increment the program counter. This is only specially for the program counter, this control signal. So this is the data path of a simple computer. Now we will see how to design using the hardware this sequence. So we know that from here, again I am going here, this is a RAM. RAM contains, what is the specification of the RAM? See here, here there are 8 address. And what is the width of the RAM? Width of the RAM should be 12 because total instruction size is 12. So width of the RAM is 12. So this is 12 and 8 means the number of the address bit is the 8. So 8 should be the number of the address. This is the 12. So what is the specification of the RAM? 2 to the power 8 into 12. This is the specification of the RAM. So the total RAM is actually 256 into 12. This is the RAM size. Clear? Signal L, I have already told, contains the bus in the loaded, is loaded to the register in the next clock cycle, and signal E is the output value of the register to the bus. Now see the what is the clock. Clock is the sequence of pulse. This pulse is generated because you already know that one micro instruction should be computed within this one pulse, and this is called one period. So if there is one micro instruction, so this to this one micro instruction should be completed within this, then here starts the second pulse, then here comes the third, this is the fourth, fifth, sixth. Okay, so this is the one time period starting from this point to this point. One pulse, this is the one time period. From here to here, another pulse or another clock. From here to here, another clock. From here to here, another clock. From here to here, another clock. And what to here, another clock. Now in designing the control unit, one type of counter is used. Why required counter here? Why counter is required here? Because here control unit has to generate the sequence of instruction. So to generate the sequence in the clock, ring counter is used. You will learn more about the ring counter in the digital. You just know here, you have to know here the ring counter, how generate the time signal. So at first it will generate T0. So T0 will be 1 and all other will be 0. Then in the next time it will generate T1. So T1 will be 1 and all the pulse will be 0. Similarly at time 2 it will generate T2. Okay, so all the pulse will be 0. Then T3 will be 1 and all other will be 0. Okay, then T4 will be 1, all other will be 0. Then last T5 will be 1, all other will be 0. After that, what happens? It will again generate T0, T1, T2, T3, T4, T5. When T5 is complete, again it will generate T0, T1, T4, T3, T4, T5. So this is the generation in the ring counter. Clear? Now see how to make. Here instruction size 12 bits. Already I have told opcode is 4 bits and address is 8 bits. Now this is the set of the instruction for this simple digital computer. See what are the instructions here? Load A, store means store A, add B to A, add means adding the data which is stored in the register to the accumulator and the data is stored in the accumulator. Then subtraction, move from A to B, data from A to B will be copied. Jump means this is the branch instruction from one address location to another. Jump means if the result of the ALU is negative, this is called jump negative, it will jump to the another address. And another is the halt means it will stop the clock pulse, that means the execution is complete. So total execution is complete if this signal is activated. So these are the corresponding opcode. You already know that opcode is 4 bit. So 2 to the power 4, that means it will generate 16 instructions, though here it is written 1 to 7 instruction. All other instruction it can be expanded here. From this it is clear that as it can generate maximum 16 instruction and only 7 instruction is given, you can expand after. Suppose you have generated one architecture, you can expand the instructions here if this is the provision. Clear? This is the execution action. What is the meaning of this? Adding, subtraction, this is the meaning. And this is the register transfer. You already know of the basic of this, that what is the register transfer operation in case of the fetch cycle and execution cycle. I told you that one instruction means a set of the register transfer operation, and using that register transfer operation or micro instruction, we can generate any types of instruction. Always remember, when we generate we want to execute one instruction, there are two types of cycle. One is the fetch cycle and another is the execute cycle. So fetch cycle is common for all this. What is the register transfer operation? PC, MAR to PC, MAR to MDR. You already know from this. MDR, memory data register, to IR, and next PC is equal to PC plus 1. So these are the set of the instruction it will generate. If the fetch, after fetch, we will go to the, if this 4 instruction from MDR to IR, it will decode. This is the 4-bit instruction because your opcode is 4-bit. It will decode the 4 bits and will generate what should be the next instruction. This is called the execution cycle. Clear? Fetch, decode, it will decode here, then it will execute. Now see here, right hand side, here the active control signal. First, it is the fetch. Fetch means MAR to PC. So I have already told, if you want to transfer the data MAR to PC, what signal you should be activated? MAR to PC. See here, MAR to PC. That means MAR to PC. So which signal should be activated? MAR data should be go from MAR to here and then from bus to PC. So we have to activate first PC signal. That means ELP. That means, see here, EP and LM. Clear? MAR to PC, EP to LM. So if I go here, EP, that means data will go from here to here. LM means MAR data to go here. One minute. EP should be activated and LM should be activated here. EP and LM. So data will go for MAR to PC. Clear? Now, actually it should be here, it is one thing wrong here. That means here the data should be come from PC to MAR. It is written wrong here. PC, because program counter contains the address, the data should be stored in the MAR. So it should be, the arrow should be from PC to MAR. So PC to MAR means EP, first EP should be activated and then LM should be activated. Because why? See here, EP should be activated. That means the contents of the program counter will go here. Then LM, that means that this data will go into the MAR. Clear? So EP to LM. Then what micro instruction? Then the next micro instruction is MDR to MDR. So here the data is read. So data is read means the read signal will be activated. So R will be activated here. Clear? After that, MDR to IR. MDR to IR means MDR data should be ED. ED means enable MDR. Then IR, that means load IR, and same time program counter will be increased. So increase the program counter IP should be activated. Clear? That means, see here the sequence. At first T0, which signal will be activated? EP and LM. Clear? T1, which signal will be activated? R. T2, which signal? T0, T1, T2, which signal will be activated? ED, LI, IP. After that it will be decoded, and the decoded it will find out then which signal it should activate. Suppose after that it goes for store operation. Store operation, that means again there are 3 micro instructions. So at T0, T1, T2 here completes, then T4, T0, T1, T2, then T3, receive EI and LM will be activated, then T4, these two will be activated, T5 it will be activated. Now see, it will be clear if I go here. So that means first it will go for the instruction register. After fetch operation, it will go to the instruction register to generate the 4-bit opcode. From the 4-bit opcode, it will go to the decoder. Okay. From decoder, it will decode which instruction will be executed. So here there are 4 bits in the instruction opcode. So what should be the decoder size? It will be 4 is to 2 to the power 4. That means 16. Out of the 16 instructions, 1 instruction will be 1. Okay, that means after the fetch operation, if opcode this is generated, it will activate 1 lines out of the 16 lines in the decoder. Clear? This is the total hardware control unit. So first I told you that this hardware control unit contains 3 components. One is the ring counter. This is the ring counter. It will generate T0, T1, T2, T3, T4, T5. Again T0, T1, T2, T3, T4, T5. Then comes the instruction decoder. I have already told you that instruction decoder decode the instruction. That means out of the 16 instruction, it will make only one instruction. That means suppose 000 not is given 001. That means suppose 001, I think load instruction will be activated. 010 store instruction will be activated. 011 add instruction will be activated. Clear? So this is the instruction decoder. It will deactivate one signal, and ring counter, it will activate only one time. Clear? Because you know 1000 0111, and this control matrix, this receives the input both from the instruction decoder and from the ring counter, and it will combine the two signals to generate the sequence of the control signal. Again, I am telling that hardware control unit contains mainly three components: instruction decoder, ring counter, control matrix. Instruction decoder will generate out of the 16 signals, one signal it will activate, one line it will activate, that means this is a signal, and it will activate one time period, and it will mix up here control section, and it will generate the control signal. And this halt, this is directly go to the decoder, it will hold the total instruction if this is 1. Okay, now see here, this is our control matrix. Clear? What are the control signals here? You know there are the 16 control signals. I have already told 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15 16. Clear? So in the 16 control signal, how to generate? Suppose at first it will generate fetch. Fetch means which is activated first at T0, EP and LM. So EP and LM both will be activated at T0. So we have written here T0, T0. Clear? Then at T1, this is the next micro instruction, R will be activated. So R will be activated at T1. Clear? At T2, ED, LI, IP, all will be activated at the time period T2. So at time period T2, see here LI, ED and IP all are activated. So fetch is complete. After that, suppose it comes the LDA, because it will decode the instruction, it will find out that the load instruction, it requires the load instruction. So load means this is the set of the micro instruction. So T1, T2, T3, T0, T1, T2 here completes fetch. Then comes T3. See here load at the T3, because this is T0, T1, T2. So T3, which should be activated if it is a load, EI and LM. So T3 here EI and LM. T3 it will be activated. T5, which should be activated, R. So T5 here in the load, it should be T5 should be R. T0, T1, T2, T3, T4. Sorry, at the T4 it should be R. So T4 it is R. Okay, and T5, which should be activated, ED and LA. See here, LA, T5 and ED, T5. Clear? So these are the signal for LDA, and these are the time period for the signal. In this way, you can generate for the all the signal what are the different time period. What only one thing is here wrong. That means instead of T3, it should be T4 here. Okay, make it sure that it should be T4 and T4. That addition, that means load accumulator will be load at the T4, not at the T3. Okay, addition will be done at the T3, but accumulator will be load at the T3. Subtraction will be done at the T3, accumulator will load at the T4. So this is the wrong. So this is the total matrix of the control signal we have generated. Clear? So if that means when this is 1, when IP is T2 is 1, IP signal will be activated. Clear? When T0 is 1, EP will be activated. When T0 is 1, LM also will be activated. When T1 is 1, R will be activated. When T2 is 1, ED will be activated. When T2 is 1, LI will be activated for fetch. Then again, LM will be activated when both LDA is 1 and T3 is 1. Clear? R will be activated when LDA is 1, that means LDA line is active, and T4 is activated. Clear? So this is our control matrix control signal. Clear? Now here, then how to generate the control matrix design? I have already told that we will go first here, IP. IP is 1. When IP is 1, T2 is 1. So here it is written IP is equal to T2. Clear? Now see here the signal W. Right. When it is activated, see go here. Signal W is activated. This signal is activated when time is T5 and instruction is STA. That means when both are 1, W will be activated. That means it will be STA and T5. So STA and T5. Clear? Now suppose LA. When LA should be high, LA should be high. See here. When LA should be high, LA should be high when LDI is high. Okay, that means LDI is T5 and add is T4. I have already told this should be T4. Add is T4 and subtraction is T4. So that means LA is equal to LDA and T5 or add and T3 or sub and T3. Sorry, T4. Again, I am telling that LA is equal to LDA and T5 or add and T4 or sub and T4. Clear? So this is our LA. Clear? So if I make this using the AND, what is the gates here use? AND gate and OR gate. See here, using only an AND gate, OR gate and AND gate, OR gate and AND gate, we design this all the control signals. See, this is here the control signal. This is the set of the instruction, and this is the time generated by the ring counter. If I make this using these gates, we will generate this. Suppose T0 at T, IP is equal to T2. That means IP when T2 is high. So IP is directly connected with T2. So see here. See here EP. EP is T0. That means T0 is 1, directly connect to the EP. Okay. Similarly, LP. LP means T3 into JMP and T, now suppose LD. LD means T4 into STA. So LD. LD is, this is STA and this is T4. So LD and STA, it will generate LD. Okay, T4 into S and STA, it will generate LD. So all the control signal is generated. See here, this is the set of the instruction, and here the set of the time signal generated by the ring counter, and using this circuit AND gate and OR gate, we generate all the control signal. That means the 16 control signal are generated. Clear? So this is the control matrix design. Now see one simple example. Suppose how we will execute the instruction. Suppose add B. Add B instruction is given. You know this instruction will have two parts. One is the fetch. After fetching, it will decode. Decode means what is the type of the instruction, then it will execute. Suppose here we have written two cycle, fetch cycle and execute cycle. So I have given here the add B. Add B means suppose this ring counter, it will generate 1 1 1 1 1, yeah, that's each of the state. So suppose this is the sequence of the control signal. At first it will fetch, at the fetch operation, first EP and LM. So when T0 is equal to 1, this control signal will be generated EP and LM. Why? See here, EP T0 is 1, EP will be activated, and again LM T0 is 1, this LM will be activated. That means T0 is equal to 1, EP LM. This first instruction will be activated. This is the fetching. T0, T1, T2, it will be fetch. So after that, the fetching instruction is the R control signal should be activated. So T1 is equal to 1. If T1 is equal to 1, see here. If T1 is equal to 1, see here, this R will be activated. So R is high now. R is activated. Then T2 is equal to 1. From here, if this table T2 is equal to 1. If T2 is equal to 1, see here ED, LI and IP. ED, here ED, T2 is equal to 1, this will be activated. Then LI, T2 is equal to 1, LI will be activated. Then IP here, IP, T2 is activated, IP will be activated. So these three will be activated when T2 is equal to 1. Then it will fetch the data. How to fetch? it will decode the data in the decoder. In the decoder, from the opcode, it will generate out of the 16 instruction, one instruction it will generate. Suppose that instruction is the add instruction, because from where it will get the add? From the decoder part. Okay, that means the opcode. It will, if you decode the opcode, it will generate one, it will activate one line. Suppose this is the add line. Okay, suppose I go here. Sorry. This add line will be activated. Okay, after this add line will be activated, what happens? Add line is activated. That means T3, now T2 is complete. T3 is 1, add is 1, because add line is activated. So T3 1, add 1. See what line is activated. T3 and add both are 1. So A will be activated. A control signal will be activated. Again, T3 and add both are 1. So EU will be activated. Clear? It's complete. Now comes the T4. When T4 here comes here, that means T4 is equal to 1 and add is equal to 1. T4 1, add 1. Which line should be activated? See here, LA. LA here, T4 1, add 1. That means LA will be activated. Clear? After that, it is complete. It will go for the T5. Here, no function here, because all function is 0. Then again, it will go to the T0, because again it will face the another signal. Clear? So this is the sequence of the instruction it will generate. So see here, you have given one set of the instruction. This ring counter will generate the different timing signal, and from this timing signal, see, this is the sequence of the instruction is generated: EPLM, R, ED, LI, IIP, A, EU, and LA. This is the sequence of the instruction, and this sequence of the instruction is generated by the control matrix. Clear? Not only control matrix, with the help of the ring counter, because without the timing signal, it cannot generate the sequence. Clear? So this is the design of the control unit. So here today I have told you that there are two types of design for control unit. One is called the hardware control unit, and another is microprogram control unit. Here we show the hardware control unit. Hardware control unit generates with the help of the three components mainly. One is the decoder, another is the ring counter, and third one is the control matrix. Decoder will, from the opcode, it will generate the particular instruction after the fetch, obviously after the fetch. Then from that particular instruction and the ring counter, that means ring counter will make one particular time period. So for that, using that sequence number, control matrix will generate the sequence of the instruction. So this is the gist of the system. So thank you for watching the video.